Bismillahirrahmanirrahim. Uh, Given the two-port network in Fig 1, calculate the voltage and current at the input and output ports. So this is the input port and this is the output port. So we need to find out the currents, voltages and currents at both the ports. Right? So we need to find out at input port V1 comma I1 and output port V2 comma I2, right? So let's first write down the equations for the hybrid parameters, as we are given the two-port network with hybrid parameters. The hybrid parameters are defined, and we have a voltage source, 100 volt voltage source in series with the 10 ohm resistance at the input port, and we have this load resistance of 50 kilo ohms at the output port, and the hybrid parameters are also given. So we have four quantities to determine, so we will need at least 4 equations to do that. So first of all, let's write down the standard equations for the hybrid parameters. So equations for the hybrid parameter V1 is equal to H11 I1 plus H12 V2. Similarly, we have I2 is equal to H21 I1 plus H22 V2. So putting the values given here in these equations, we'll get 2 equations. So substituting values, H parameters. So we have V1 is equal to H11 is 2 kilo ohms, so that is 2000 I1, and plus H1 is 10 to the power minus 4, so that is 10 minus 10 to the power minus 4 V2. Let me call this equation 1. Then we have I2, and I2 is equal to H21 I1. H21 is 100, so 100 I1, and plus H22 is 10 to the power minus 5. Yes, H22 is 10 to the power minus 5 V2. So we have these 2 equations, but we need to determine these 4 quantities, V1 I1 and V2 I2. So we need another 2 equations. So applying KVL at the input port and at the output, we'll get 2 more equations. So KVL at input port. So this gives us minus 100 plus 10 I1, right, plus V1 is equal to 0. So we can write this V1 is equal to 100 minus 10 I1. So that is our equation number 3. So we have another equation, right? 3 equations. And now at the output port, KVL at the output port, KVL at output. This gives us 50 kilo ohms, so 50,000 I2 plus V2 is equal to 0. So V2 is equal to minus 50,000 I2. Let me call this equation number 4. So now we have 4 equations. So we can solve these 4 equations simultaneously by any of the standard methods to obtain the values of V1, I1, V2 and I2. So for example, I have this V1 here is equal to this value, and we have V1 here equal to this value. So we can substitute this value here, comparing both equations 1 and 3. So comparing 1 and 3. So this will eliminate V1, right? So this is 100 minus 10I1, and 100 minus 10I1 is equal to 2000 I1 plus 10 power minus 4 V2, right? And that is 100 is equal to 2010 I1 plus 10 power minus 4 V2. So let me call this equation 5. So this equation is only in two variables. So if we get another equations with the same variables, so we can solve them these two equations simultaneously to get the values of I1 and V2. So to this end, let's look at this equation. I2 is equal to 100 I1 plus 10 power minus 5 V2, and V2 is equal to minus 5000 I2. So let's substitute 2 into 4. So 2 in 4 gives, so V2, this will eliminate I2, right? And this will give us equation in terms of I1 and V2. So we have V2 here, and I2 substitutes for I1 and V2 here, right? So V2 is equal to minus, and this will be equation in these two same variables which this equation has, equation 5. So we can then solve these equations simultaneously to arrive at to find out the values of I1 and V2. So minus 50,000, and this is 100 I1 plus 10 power minus 5 V2, right? So this is V2 is equal to minus 5 into 10 power, this is 5 into 10 power 4, and that is 10 power 2, so that will be 10 power 6 I1, right? And here we will have minus 5 into 10 power 4 into 10 power minus 5, so that will leave us with minus 5 into 10 to the power minus 1 V2, right? So this is V2 and this term is V2, so we can combine them together. So this is basically 5 over 10, so this is 0.5 V2. So this is basically then V2 plus 0.5 V2, right? V2 plus 0.5 V2, and that is equal to minus 5 into 10 power 6 I1. So that is 1.5 V2, and that is equal to minus 5 into 10 power 6 I1. So then V2 is equal to minus 5 into 10 power 6 divided by 1.5 I1, and V2 is equal to, so we'll need calculator here now. So 5 into 10 power 6 divided by 1.5, so that leaves us 5 divided by 1.5, so that is 3.33 minus 3.333 into 10 power 6 I1, and let me call this equation number, this was 5 here, so that is equation number 6, right? So we now have V2 is equal to minus 3.33 into 10 raised to the power 6, right? So we have expressed V2 in terms of I1, right? And we have this equation 100 is equal to 2010 I1 plus 10 to the power minus 4 V2. So this equation 5 is in terms of I1 and V2, and this equation 6 is in terms of I1 and V2. So we can solve them simultaneously. So we can substitute the value of 6 in 5. So 6 in 5 gives 100 is equal to 2010 I1 plus 10 to the power minus 4, and we substitute the value of minus 3 V2 minus 3.33 into 10 to the power 6 I1. So that will be 100 is equal to 2010 I1, and that will be minus 3.33, right? And that is 10 to the power 2, 10 to the power minus 4 into 10 to the power 6 leaves us with 10 to the power 2 I1. So 100 equals 2010 I1, and that is basically 333.33, because it is repeating, it's a recurring decimal fraction. So 333.33 I1. So 2010 minus 333.33, that is 1676.67 I1 is equal to 100. So I1 is equal to 100 divided by 1676.67 amperes, and that is 100 divided by the same quantity, and that is 0.05964 amperes. So when the quantity is small, we should write at least few decimal places, right, to be more precise. So this gives us the value of I1, and let me call this equation 7, right? And from this I1 we can find out the value of V2, right? We can substitute the value of I1 here in equation 6. So this will give us V2. So putting 7 and 6, so that leaves this, that gives us V2 is equal to, that was minus 3.33 into 10 to the power 6 and into I1. So I1 is 100 divided by 1676.67. So that is V2 is equal to, calculator again. So we already calculated this fraction, and this was found out to be 0.05964, and that is multiplied by 3.33 and into 10 raised to the power 6. So that gives us minus 198804.77 volts. So we get the value of V2 as well, right? So let me call this equation 8. So we have found out the value of I1 and V2 so far. So now we can find out the value of V1, for example, from here. We can substitute the value of I1 here and find out the value of V1. So putting I1 was in equation 7 in 3, equation number 3. So V1 is equal to this equation here, 100 is minus 10, and I1 was 100 divided by 1676.67. So V1 is equal to 100 minus 10 into 0.05964. So that gives us 99.4036 volts. So we have found out the value of V1, we have found I1, we have found I2, and we are left with I2 now. So to find I2, I think we can use this equation, equation 4, right? So putting V2 in 4, we will get I2. So sorry, this was 8 and this is 9. So 8 in 4 gives that is V2 is minus 1988804.77. V2, that is V2, and V2 is equal to minus 50,000 I2, right? So I2 is equal to 1988804.77 divided by 50,000. So calculator once more, 1988804.77 divided by 50,000. So that gives us 3.976 amperes. So I2 is equal to 3.976 amperes. So we have found out all the 4 parameters. We have found out V1 99.4036. we have found I1, that is 0.05964 amperes. Current at the input port is very small, and we have find out V2, which is quite a large voltage, minus 1988804.77 volts, and we have found out the current I2, 3.976 amperes. So this is all the 4 parameters we have determined by using the given H parameters and the circuit conditions at the input and the output port. So we can actually find out all these parameters using an alternate method as well. We can draw the equivalent circuit for the H parameters. So you see, we have H11 is the input impedance, right? And H12 is the reverse voltage gain, right? And H21 is the forward current gain, and H22 is the output admittance. It is the admittance at the output, and this is the impedance at the input. And we have the voltage gain, and we have the current gain, forward current gain. So using these values, we can devise an equivalent circuit, equivalent network. So for example, at the input port, we have the input admittance impedance. So this is H11, right? And then we have H12, right? So H12 is basically reverse voltage gain. So this is V1 divided by V2, So V1 divided by V2. So if we need to have V1 here, so H12, which is V1 divided by V2, it should be multiplied by V2 to give us V1 here. So this is voltage controlled voltage source. So this is the input, and at the output we can similarly have current source, controlled current source, due to the forward current gain. And at the output, H22 is admittance, so the admittance can be defined by this equation here. So this is H22, right? So H22, and this will be H21I1. This is H11, right? H11, H12, H22, and this is H21. And if this is to be I2 and V2 and I1 and V1, so H21 is I2 divided by I21. H21 is I2 divided by I1, right? So if this is to be I2, so this should be multiplied by I1, right? So let me call this equation 2, figure 2, sorry. So this is the equivalent model for the H parameters, right? So using this parameter model, we can find out these values using by employing circuit analysis techniques on this equivalent model. So we can substitute the values of H11, H12, and we can imply the given circuit at the input port, at the input port and the output port, and then find out the parameters. So let me redraw this circuit again by using the conditions here. So at the input port we have this. Let me connect this voltage source here, right here. So this is 100 volt source in series with 10 ohm. This is 10 ohm, right? And we have this 100 volt source at the input, and at the output we have this is minus plus, right? And we have this load resistance, and this is 50 kilo ohm. So H22 is basically 10 to the power minus 5 Siemens, so that will be 10 to the power 5 ohm, right? 10 to the power minus 5 Siemens means 10 to the power 5 ohm impedance. So H21 is 100, so this is 100 I1, right? And H11 is 2 kilo ohm, so H1 this is 2000 ohm, and H12 V2, so H12 is 10 to the power minus 4, so that is 10 to the power minus 4 V2 here, this controlled source. So now we have this equivalent circuit, and we can apply circuit analysis techniques to basically find out the values V1, I1, V2 and I2 here. So for example, if you apply KVL in this left loop, right? So KVL in the left loop, so this is minus 100 and this is 10 plus 2000, so that will be 2010 plus 2010 I1, right? And plus H1 to V2, that is 10 to the power minus 4 V2, and that is equal to 0. And that gives us, let me call this equation number 10 now, right? So this is one equation we have, but this is in terms of only two variables, I1 and V2. And this is the voltage V2 across this branch also, across this branch also. We can combine both these branches. So let me call this Z2, and that is 10 power 5 in parallel with this 50 kilo ohm resistance. So that means 10 power 5, that is 100,000 multiplied by 50,000 divided by 100,000 plus 50,000, right? And that is Z2 is equal to 100,000 into 50,000 divided by 100,000 plus 50,000. So that is 3.33 recurring decimal into 10 raised to the power 4, 10 power 4 ohms, right? So this is the equivalent resistance at this of these two branches. And now note that when these are two combined together, the current flowing here is the same current will flow through this equivalent branch. So V2 will be equal to minus this 3.33 into 10 power 4, because the direction of current is this way, so we'll take a minus sign here, right? So this impedance multiplied by this current, so this is 100 I1, right, multiplied by 100 I1. So V2 is equal to minus 3.33 into 10 power 6 I1. So let me call this equation 11. So we have this equation V2 in terms of V2 and V1, and we have this equation also in terms of V2 and I1. We can substitute the value of V2 here. So 11 in 10 gives us minus 100 plus 2010 I1 plus 10 power minus 4 into V2. So that is minus 3.33 into 10 power 6 I1. So that is minus 100 plus 2010 I1, and that is minus, right, minus 3.33, and that is the recurring decimal, and 10 power 6 into 10 power minus 4, so that is 100 I1, right? So that means yes, and that is equal to 0, right? That is equal to 0. Minus 100 plus 2010 I1 plus 10 power minus 4 V2, we substitute the value of V2 here, and that is equal to 0, right? And this is equal to 0. Minus 100 plus 2010 I1 minus 3.3 into 100 I1. So 2010 I1 minus 333.33, right? 300, because this is a recurring decimal, 333.33. So that is 1676.67 I1, right? And that is equal to 100. So I1 is equal to 100 divided by 1676.67, and that is equal to, we already found that out, once more, that is 0.05964 amperes. So we have determined the value of I1. So let me call this equation 12, right? Equation 12. So putting 12 in 11, it gives us the value of V2. So V2 is equal to minus 3.33 into 10 power 6 into I1, and that is 0.05964. so V2 is equal to 3.33 into 10 to the power 6, and that is minus 198,607.96 volts. Minor difference from the previous found value, right, due to the propagating error, right. Incidentally, if we find 3.33 into 10 power 6 into this value, 100 divided by 1676.67, no, 3.33 into 10 power 6, right, and into 100 divided by 1676.67, so that will again result in this same value, 198,607.96 volts. So V2 is this value. We have found I1 and we have found out V2 also. So we need to find out V1 and I2 now, right? So we can for example use KVL in this left loop. So V1 is equal to this 2000 I1 and plus this value V2. So I1 is known and V2 is known, and we can find V1. So KVL in left loop again, but not in the full loop. We imply KVL from here now, right? Not KVL in this entire loop from here. So we know this voltage across these two terminals is V1. So just here we apply KVL. So KVL in left loop. So this will give us minus V1 plus 2000 I1 plus 10 power minus 4 V2 is equal to 0. So we can put in the value of I1 and V2 here. So V1 is equal to 2000 I1 and plus 10 power minus 4 V2. So V1 is equal to 2000 and I1 is 0.05964 plus 10 power minus 4, and V2 is minus 198,607.96. So V1 is, so this is into 10 power minus 4, right, and we need to subtract this value from 2000 multiplied by 0.05964, right, and minus the previously found value. So that gives us 99.42 volts. So V1 is 99 that's the same value, right, almost the same value. So we have found out V1 now. So we can find out, we have found out I1, we have found V1, we have found V2, we are left with I2 now. So for I2 we can apply KCL here. So KCL at this node. So KCL at this node, I2 is equal to then V2 divided by 10 to the power 5 plus 100 I1. So let's do that. So KCL at the right side. So I2 is equal to V2 divided by 10 to the power 5 plus 100 I1. So we just need to substitute the value of V2 and I1 here. So V2 was found out to be this, minus 198,607.96 divided by 10 to the power 5 plus 100, and I1 is found out to be 0.5964, right? Yes. So I2 is equal to minus 198,607.96 divided by 10 to the power 5, sorry, that is 10 to the power 5, right? And plus 100 into 0.05964, and that is equal to 3.98 amperes. So this was 12, let me call this 13, equation 13, this was 14, and this is now 15. So let us compare the values, these with the previously found values. So we first found out I1, and that was equal to 0.05964 using the first method, and using the second method also I1 is the same value, 0.05964, right? And then we found V2, this is minus 198,804.77, and we found out V2 here using this method, minus 198,607, slightly different value but almost similar result, right? Then we find out V1 99.403, so this is the same value approximately, right? And then I2 is 3.976, and we have now arrived at 3.98, which is the same value, right? So we have found out all the four parameters. So let me summarize them. So V1 is equal to input port. V1 is 99.4036 volt, right? And I1 was 0.05964 amperes. So at the output port, V2 is minus 198,804.77 volt, and I2 is 3.98 amperes. So these are the values that we needed to find. So once we have found out these values, we can calculate actually different ratios. For example, we can calculate the voltage gain, V2 divided by V1, right? So for example, V2 here is minus 198,804.77, and V1 here is 99.4036. So V2 divided by V1, which is the voltage gain. So minus 198804.77 divided by 99.4036. So the voltage gain is minus 199.98. Similarly, we can find out the current gain. So I2 divided by I1. So I2 is 3.98 and I1 is 0.05964. So I2 divided by I1, the current gain is 3.98 divided by 0.05964, and that is equal to 66.73. Voltage gain and current gain we have found. Similarly, you can find the input impedance and the output impedance. So input impedance, for example, V1 divided by I1. V1 is 99.4036 and the current is 0.05964. So the input impedance V1 divided by I1 is given by 99.4036 divided by 0.05964, and that is 166.73 ohms.